Good evening, everybody. I'm Rick Gehring from the Naperville Astronomical Association, and tonight we're going to be talking about the moon. You can see on the picture of the moon that's on the screen with me the route we're going to be following tonight, and the things we're going to be looking at have been marked on there if you want to follow along. And now just sit back and relax, and let's have a nice hour of lunacy. Visual astronomers like us have a love-hate relationship with the moon. Sometimes it delights us when we have a chance to look at its fascinating topography, and the moon's topography is indeed fascinating, as we're going to see tonight. Other times it just plagues us, especially when it's marching towards full moon and it acts more and more like an unwanted mirror in the sky, reflecting secondhand sunlight into areas that we'd rather have dark and washing out our views of fainter targets. When that happens, the moon just sort of starts acting like a playground bully, chasing all the other kids out of the park. Tonight, however, it's nowhere near full moon, so let's see if we can let it delight us for a while. But before we do that, let's get to know it just a little bit better. The first thing that's obvious about the moon is it is very nearly a perfect sphere. If you measured the circumference of the moon around its middle, around its equator, it would be 6,786 miles. If you measured it from pole to pole, its circumference would be 6,776 miles, which means that it's within 10 miles of perfect, which is closer than you or I are likely to be. It's also about 1/6 as wide as the Earth, or 1/6 the diameter of the Earth. And its gravity is also about 1/6 of Earth's gravity, which would be nice, since if you weigh 150 pounds here, you'd only weigh about 25 pounds there. So we're all skinny in Earth in moon weight. A lot of people don't realize this, but the moon's size does not change at all depending on where it is in the sky. People who see the moon near the horizon often think that it looks much bigger than it does when it's high in the sky, but that's an optical illusion, and it happens because when the moon's near the horizon, we can see things on the ground that we can compare it to, and it looks very big compared to them. On the other hand, when it's high in the sky, there's nothing to compare it to, so it looks much smaller. And you don't have to take my word for that. You can prove it. Next time you see a big moon by the horizon, stick your hand out, your arm out in front of your face, raise your thumb, and put it over the moon, and you'll find that the moon fits behind your thumb just about perfectly. Then the next night or later that night when the moon's high in the sky, do the same thing, and you'll find out that your thumb covers up the moon exactly the same way, no matter where it is in the sky. Now, the moon's size does change depending on how close it is to us in its orbit. And that's why you sometimes hear the people on the news talking about a supermoon. The moon's orbit varies from about 225,000 miles away from us when it's close, and about 250,000 miles away from it when it's far away. So there really isn't all that much difference between its close distance and its far distance. Either way, it takes light about 1¼ seconds to get here from the moon, so you're always looking at the moon while it's 1¼ seconds younger than you are. But since the distance is so close, the supermoons really aren't all that super. The maximum difference in their size is about 14%, and that's the difference between something looking like it's 30 inches wide and looking like it's 34 inches wide. Even during a supermoon, if you try sticking your thumb out, you'll find out it still fits very easily behind your thumb. Now, when we see things on the moon, we see them because of the interplay of lights and shadows. And features on the moon are easiest for us to see when their shadows are longest. Now, just like on Earth, the longest shadows on the moon happen around sunrise and sunset. And when we look at the moon, we can see where sunrise and sunset are happening, because we can see the line that divides night and dark, light and dark, day and night, sunrise, sunset. And that line is called the terminator, even though it doesn't look at all like Arnold Schwarzenegger. Now, if we could go to the live shot of the moon, which Drew Carhart has in his telescope in Naperville in his backyard right now. Hopefully we're going to get it up here in a moment. There it is. Okay, and Drew, if you could pan a little bit to the east, away from the terminator, you can all see the dark part of the moon on the left side of the screen, and then the light part on the right side, and the terminator is the line where those two meet. But as Drew moves farther away from the terminator, I want you to notice how things near the terminator look very sharp and very in focus. And the farther away we get from the terminator, the more they get washed out, and everything just seems to become kind of flat and uninteresting. So that illustrates how the shadows make the view for us on the moon. So everything we're looking at tonight is going to be right along the line of that terminator. We'll start at the north end and move down to the south end. Now, if you can move just a little bit farther south, Drew. And a little bit back towards the terminator. Not okay. Okay, good, excellent. All right, so what we can see here on the moon is a curving mountain range that sort of starts towards the top. Let me see if I can mark it for you. Give me a moment. It starts up here, which is not marking. Sorry. Let me try this again. It starts where I just put the red dot up there, follows down past that line here that we're going to talk about in a couple of minutes. It's not making a mark. Well, I'm do it without marking it then. So we have a curving mountain chain. Now, mountains on the moon don't happen for the same reason that mountains happen on Earth. On Earth, mountains generally happen from the movement of the tectonic plates under the ground. On the moon, that isn't happening. Mountains on the moon are almost always the rims of old, huge impact craters. So what we're seeing here is the mountain range on the moon called the Lunar Alps, and it marks the northeast corner of a very large impact feature called the Imbrium Basin. You can see inside the curve of the mountain chain, you can see that dark, flat-looking surface, and that's the surface of Mare Imbrium. Now, when early moon map makers first looked at the moon, they saw, of course, the light areas and the dark areas, just like we do, and they decided that the light area, or the dark areas rather, must be oceans and seas. So on the early moon maps, there are 20 different named seas, an ocean, a few marshes, 10 bays, and 17 lakes. But as it turned out, none of those things are actually full of water. All of those dark features are actually dark solidified lava that flowed up from inside the moon, either as a result of volcanic activity like we have on Earth, or usually from large impacts hitting the moon and the floor cracking and the lava flowing up through the cracks in the floor of the impact basins. Nonetheless, those areas are still called mares, which is the Latin word for seas, since that's what they called them starting in the 1600s, and it's stuck with us. And each of these large seas is over 300 kilometers wide and was formed when a huge impact struck the moon and later flooded with lava many miles deep. So the first feature that we're going to look at is a gash that you can see crossing the lunar Alps there. Thank you, Jim. In that view, it's called the Alpine Valley, and it's one of many valleys that we find on the moon. But again, valleys on the moon don't happen for the same reason they happen on Earth. On the moon, valleys happen generally for two reasons. Either they happen where the moon's crust has subsided between two raised areas along a pair of fault lines, or in some instances, valleys occur when the material that's blasted out of a crater during an impact, when it doesn't get very high in the air, and it literally just plows itself through the surrounding terrain. It's a little unclear exactly how the Alpine Valley formed. It's most likely a depressed area between two raised fault lines, but its direction away from the Imbrium Basin would be consistent also with it being caused by material that was pushed out of the basin during the Imbrium impact and disrupting the terrain around it there. Now, if we can go a little bit farther south, from the Alpine Valley, we see out in the mare, we see a bright white spot, and that's a solitary mountain called Mount Piton. It's not part of a mountain chain on the moon. It's fairly unusual for there to be solitary peaks on the moon, but there are a number of them. Mount Piton has two distinct peaks. You can sort of see two parts of it here. Excuse me, but you can't see it in quite as much detail as I would like. That mountain is a little bit over 1.25 miles tall, sticking right up from the lava of the Imbrium Mare, and taking into account that there's probably 2-3 miles of lava that it's sticking out from, it originally would have been nearly 5 miles tall. Now, if we look down and to the right from Mount Piton, we see a nice big detailed crater. Unfortunately, right now it's getting a little bit too much sunlight on that left side, so we're just seeing a sort of a white glare over there. Craters on the moon, with only one exception that I know of, all of the craters on the moon were formed by impact events, they're not extinct volcanoes as was once thought. Something really big hits the moon and it leaves a hole is basically what happens. There are two kinds. One is called a simple crater. One's called a complex crater. Simple craters are kind of what you would expect them to be. They're very smooth. They look sort of like a cereal bowl in the ground. You can see two nice examples of simple craters right up above the Alpine Valley. they tend to be very small. They are almost by definition never more than 20 kilometers in diameter. And the reason is that once the crater gets over 20 kilometers in diameter, the material on its walls can't hold itself up anymore, and it starts to slump inward, and it creates what's called terraced walls, where the walls, instead of being smooth like they are in the bowl craters, they kind of come down in a stepwise fashion, almost like if you've seen the pictures of the race fields on the sides of hills where they come down in steps, almost like a pyramid. You can see some terracing pretty well. There's a large crater just above and to the right of the Alpine Valley, where you can see on the right-hand side, you can get a sense of the terracing in the walls on the side where the sun's not too bright. The other thing that happens with a complex crater that does not happen with a simple crater is a central peak or a group of central peaks. What happens with the large impacts that cause complex craters, the moon's crust is pushed inward by the force of the impact, and immediately afterwards, the crust rebounds back outward. And it rebounds outward with the center of the rebound's force at the center of the crater, and that creates a peak in the center. The central peaks in large craters are generally between 1.5 and as many as 4 kilometers tall above the crater floor. So they're pretty impressive things. Now, if we can move just a little bit south again, please, Drew. Not much, but a little bit. That would be fine. Come back. Okay. If you look right above the crater we were talking about earlier with the bright left wall, you can see another crater that looks very different from the ones we've been talking about so far, and it has 2 simple craters inside it. And that's the one right there. That crater is called Cassini, and it marks the southeast end of the Lunar Alps, but more importantly, it's what's called a flooded floor crater, which means that it started out in life as a complex crater with terraced walls and a central peak, but somewhere along the line, the floor of the crater cracked open and lava welled up from inside the moon. Or in some instances, although this did not happen with Cassini, in some instances, mare lava flows have sometimes washed over the edges of pre-existing craters and filled them in that way. Cassini is interesting because so much lava pushed up through the floor of Cassini that by the time it was done, the floor of the crater is actually higher than the surrounding terrain. You can get a sense of that from looking at this image here. It actually looks like the crater floor is higher than the terrain around it, and that's because it is. There's many miles of lava inside the crater. The lava is thick enough that the central peaks of that crater were completely buried, and it's really an impressive display of filling stuff up. Now, if we can go just a little bit farther south, we're going to make a stop at one place that we can't see well. We're going to talk about it anyway because it's important. Let me see if I can make a mark with the spot I'm looking for here. No. All right where that arrow's pointing, you can see, well, you could when it was pointing there, right below the arrow now, there are two bright spots, almost like the sides of a doorway. And if you go through that doorway from left to right, you'll be in a little protected area where Apollo 15 landed. Inside that area, there's what's called a rill. We're going to see some rills in just a couple of minutes, but basically a rill, when we can see them, sort of looks like somebody laid a thread across the floor of the moon. It's a very thin line from where we're sitting. It's usually, a mile to 3 miles thick, and it's a place where, while lava was flowing across the moon, the lava dug itself a channel in the ground because it's much heavier than the pre-existing terrain, so it tended to sink. And sometimes these channels would roof over while the lava was still flowing, forming a lava tube. After the lava stopped flowing and the tube became empty, there was nothing inside it to hold it together, and the roofs tended to cave in, and the leftover structure, these little channels that were left in the terrain, are called rills. The folks who were on Apollo 15 was the first trip to the moon that brought the lunar rover along with it. And Dave Scott and Jim Irwin, who is not the same Jim Irwin who's doing our engineering tonight, but a different Jim Irwin, drove the lunar rover right up to the edge of that particular rill, which was about 1,000 feet deep. And to put it mildly, they did not have there were no guardrails up there, so they had a pretty good time. Before we leave this area, there is one feature I would like to show you right where, just to the right of the two paired craters with the bright rims. Just to the right of that, you can see what looks almost like a little wrinkle in the floor of the mare. If you could drop down a little farther south, Drew, so we can see that right exactly there. Okay, and that is something called a wrinkle ridge. We see them a lot on the moon. They happen in mares, or what used to be called seas. And what's interesting is that they look for all the world like waves on an ocean. And in a way, they sort of resulted from a almost similar process. When the mare was flooded with lava, the lava was much heavier than the crust underneath it, and the center of the mare, where the most lava was, tended to push the crust underneath it down. As the lava was cooling and solidifying, the crust falling down under the center sort of caused the lava to kind of push in concentric rings towards the center and form these ridges where partially cooled lava flowed over the tops of the existing lava. And the wrinkle ridges therefore tend to follow the coastlines of the mare, much as this one does. You can see it's curving a little bit in the same direction as the coastline of Mare Imbrium that it's part of. So if we can head a little farther south, see where we're going next. All right, we have again another mountain chain. This one's starting sort of the lower right arc of Mare Imbrium. It's called the Lunar Apennines, and those are about 5 kilometers tall, measured from the surrounding surface, or about 3 miles, 3 miles above the ground. Now, if we head a little south from there, we're going to find probably the best example of a rill on the moon. Actually, right there, Drew. Whoa, can we? Right near the top of the screen. I wasn't going to bother with this, but it looks so good in this view. There is what looks for all the world like a ram's footprint. That I don't know if you can mark it, Jim. It's just above that rill. There we go. That was given the name Aries hoofprint back in the 1600s by some of the very early lunar map makers who thought that it resembled the hoofprint of Aries. Right underneath it, you can see a sort of a bent line, which is Hyginus Rill. Again, it's right. It's got that little crater right in the bend. It's a collapsed lava tube where lava was flowing before the mare hardened, and that crater may be the only crater on the moon that, in fact, resulted from volcanic activity rather than from an impact. Not only is it right in the middle of a lava tube, which is obviously a volcanic structure, but it also goes only down, not up. You can see all the craters around it. You can see the walls are up above the surrounding terrain. That particular crater has no walls above the surrounding terrain, which makes it much more likely to have been volcanic rather than due to an impact. Just south of Hyginus Rill, if you use the shape of the rill as an arrow pointing southwest, you come to a crater. And just to the right of that crater, we may need to go a little farther south to be able to see it, Drew. But just to the right of that crater that it points to, there's another series of rills, much more subtle, but we can see them tonight, so we might as well spend a moment looking at them. Whoops, where did we go here? There we are. Okay, it's now up in the top left part of the view that we have here. That crater is called Triesnecker. The rill system is called Triesnecker Rill, and the Triesnecker Rill is formed in the shape of a K. We can't really see the long vertical part of the K, but we can see the arms to go up to the right and up down to the right from there, forming a little V shape just to the right of the crater. So again, it's another rill system with collapsed lava tubes. There is a crater to the left of there that I thought we might be able to see something neat on, but I think we're a little bit too late because the light is not in the right position for it. So let's continue, and where are we going next? Let's head a little bit farther south, please, Drew. We're now going to spend a couple minutes with some craters that are right along the terminator. You can see there's one of them is running out of the bottom of the view. So if we could go just a little bit farther south to put it back in, we have three of them, three large craters on top of each other, right along the terminator. and all three of them are just remarkable, but unfortunately right now they're awfully dark. But what's interesting is the two southern ones have tall central peaks, and you can see that the sunlight is hitting the central peaks on both of them long before it lights up the floor of the crater. So if you can imagine standing on the floor of the crater, which is about 3 kilometers below the walls and 3 or 4 kilometers below the tip of the central peaks, sitting there in the dark, looking up and seeing the central peak glowing in sunlight, it would probably be quite a sight. You can also get a little bit of an idea of the intricate terracing on the walls, particularly in the way that the west wall is lit up on the bottommost of those 3 craters. You can see a lot of looks like knotted rope kind of shapes in there, where the terracing is throwing shadows and highlights. To the right of the top crater is another complex crater called Albategnius. It has a wonderful triangular central peak that is being lit very nicely by the sun right now. So you get a sense of its size and how impressive it must look up close. There's also at the north end of the crater, right above the central peak, there are 3 little simple craters that formed after Albategnius was formed, and I kind of like the fact that the 3 of them make a neat little snowman figure up there in the top of the crater. There is also right in the, there we go. Yeah, there's a snowman, and there's actually to the left, although we don't have quite enough resolution to see it well, there's also a candy cane of craters over there to the left. So it's kind of a neat Christmas thing. Unfortunately, now it's not Christmas. So let's let me see where I was going next.
Hey, Rick, there's kind of a question on Facebook that maybe you can ask. So someone asked, how big are these craters compared to a meteor crater on Earth?
I don't remember how wide Barringer crater is, but the ones that we're looking at, to give you an idea, those 3 in a row that we're just looking at, the one on the top is 95 miles wide, the one in the middle is 73 miles wide, and the one on the bottom is 60 miles wide. And that one over to the right, Albategnius with the triangular central peak inside it is 85 miles. So they're pretty big. It'd take a while to drive across them, and I wouldn't.
Rick, Barringer crater is almost exactly a kilometer across, so a little over 7/10 of a mile. So.
Okay, so compared to Barringer crater, these are what, 7/10 versus 60 to 95, 100 times as big, or 100 times as wide. Am I doing my math right? Yeah. So 100 times as wide, 100 times in both directions. So the area of these compared to meteor crater in Arizona would be 100 times 100, or 10,000 times as much floor area as that crater shows. Okay. All right, let's see if we can head a little farther south. There's really not too much yet to go. Let's see where we're at. Okay, you probably went a little bit too far. come up a little bit. Where am I here? Bear with me for just a minute. Drew, a little farther south. Why? Just a hiccup north. Okay. All right. Some of the things that I was seeing earlier, there's too much shadow now. However, let's look at, there's a crater. Well, let's see what I can do here. Okay, we want to look at, actually, popping into view again. Let's look over at these guys. Okay, right where I just put the arrow, you can see there's a crater sort of on top of another crater, and then above that crater, there's two little ones that almost look like ears. Okay, so I'm looking at the two craters right underneath the ones that look like ears, and what I want you to look at is the way the lower crater obviously happened after the upper one. And we can tell that because of the way the lower crater, which is okay, lower crater down here. All right. If you look at how it interacts with the crater right above it, you can see where the lower crater literally pushed the south wall of that upper crater forward. And if we had a little bit better view, we'd be able to see how it pretty much just knocked the wall of that crater above it right onto its floor. And we can see exactly the same thing happening just to the right of those craters. If we look at this large crater right there, and right where Jim just put the blue arrow, you can see we have to move a little bit to the east to keep it in there, Drew. But you can see where that subsequent crater to its right literally just knocked its wall, knocked the east wall of the earlier crater onto the ground and kind of spread it across the crater floor. Then one more before we call it a night. If we go just a little bit south, Drew, what I'm looking at is partly in the view, but not entirely. Okay. Right, we have a series of craters right there. Well, come on, okay. And just to the right of the arrow, you can see what looks like it looks almost like a three-part crater. There's a section at the top that has two parts, one on the left, one on the right, and a perfectly straight line down the middle between them. And then the bottom is another crater with a V-shaped northern wall. And it's a little unclear, no, not there. That's actually above the formation I'm looking at. So we've got the right where the arrow is, points to the top of that straight wall, and then if you see down at the bottom of that straight wall, there's the curving south wall, or north wall rather, of a crater lower in the view. And it's very unclear, how those particular craters happened. Most likely, best guess is that the parts that are left and right of that that straight line happened at the same time with a simultaneous impact of two different chunks of stuff, likely something that broke up just before it hit the moon and made simultaneous craters to the left and right of the divider, and then the one underneath it happened later. The nice part is that the light isn't exactly right for it now, but about an hour ago, the light showed those three features as making either a peace sign or a Mercedes logo, whichever you prefer. It's another nice little marking on the moon. So that pretty much brings us to the end of what I had to show you tonight. Not sure if there's any other questions out there, Jim or Kurt or whoever's doing the questions.
No questions.
Nobody? Okay. Well, thanks for joining us tonight. Hope you had some fun becoming a lunatic, at least for a half hour or so, and maybe you even learned a thing or two along the way. Our observatory public nights are still on hold due to social distancing, but someday we'll be able to open up our space again, and I hope you can join us under the stars when that happens. Until then, try to get outside once in a while and see what's up. That's what I'll be doing, and I hope you'll take some time to do it too. Good night.